Welcome back everybody, this is Mr. Navarrete, and today I'll be going over the Predicting Thermodynamic Change handout. This one is going to require some thinking, so let's get started. For our first question, we want to figure out what the enthalpy would be, the entropy, and our free energy of the phase change from liquid water to vapor at 298 Kelvin. Now 298, that's room temperature, so would it spontaneously, a glass of water, go from liquid to gas? Well, I haven't seen that happen, so I'm going to say that it's not going to be spontaneous. The phase change from liquid to gas, you're going from low disorder to a higher disorder, so your entropy is going to increase. And because it's going to be a phase change from liquid to gas, well, I know that it's going to be an endothermic reaction. I'm going to need to add heat. So my enthalpy is also going to be positive. Number 2 might look like a very similar question, but we have to notice the change in temperature. Now we're at 374 Kelvin, which is a little bit above boiling. So would at over 100 degrees Celsius, would my glass of water go from liquid to gas? Yeah, it definitely would. So it is spontaneous. My entropy, because I'm still going from that phase change of liquid to gas, it would still increase. And my enthalpy, since it is going through that phase change, I do need to add heat, so my enthalpy would also be positive. For 3, again, we're at room temperature, but now we're going from liquid to solid. So have you ever seen a glass of water at room temperature go from liquid water to ice? I haven't, so I know that it's not going to be spontaneous. My entropy, because I am going from higher disorder to more ordered, it will decrease. And in order to go through that phase change from liquid to solid, it is going to need to be releasing some of that heat. So my enthalpy would be negative. 4 looks very similar. We're still at room temperature, but now the phase change is going from solid to liquid. So if you have ice in a glass or just anywhere at room temperature, would it go from solid to liquid? Yeah, that's melting. So that is going to be spontaneous. My entropy, because I'm going from solid to liquid, I'm going from low disorder to more disorder, my entropy will increase. And to go from solid to liquid, it is going to have to absorb some heat. Enthalpy is going to be positive. Now 5, it might look a little tricky because it says carbon dioxide, solid to carbon dioxide gas, but that's just dry ice. And we've had dry ice in the classroom. So would dry ice at room temperature, would it go from a solid to a gas? And yeah, it does. It'll immediately sublime. My delta G is going to be negative. Will be spontaneous. Going from solid to gas, I am really increasing my entropy. So that's going to be positive. And my enthalpy, in order to go through that phase change, it needs to absorb heat. So my enthalpy will also be positive. For 6, we are told that our reaction is spontaneous. So immediately that lets me know that my delta G is negative. So now we just have to figure out our enthalpy and our entropy. Well, entropy, we have 1 mole of calcium oxide and 1 mole of sulfur dioxide going into 1 mole of calcium sulfate. We're going from 2 moles to 1 mole. I'm decreasing my entropy. That's going to be negative. So now we just have to figure out whether our enthalpy is going to be positive or negative. And for that, we're going to have to use the relationship between free energy, enthalpy, and entropy. My relationship states that my free energy is going to be equal to my change in enthalpy minus my temperature times my entropy. So I already know that my free energy is negative. And my entropy is also negative. And if I have a minus times a negative, well, this whole term will eventually become positive. I know that my enthalpy, whatever has to be there, needs to be negative in order for this relationship to be true. And because of that, that's going to tell me that my enthalpy is going to be my driving force. For 7, Well, we are told that this reaction is not spontaneous. So that's going to tell me that my free energy is going to be positive since it's not spontaneous. We are going from 1 mole of a solid to 2 moles on this side. So 1 mole of magnesium oxide and 1 mole of carbon dioxide. We are increasing our spontaneity. So that's going to be a positive entropy. And now again, we have to figure out what my enthalpy is going to be. And we can use, again, our same relationship between free energy, enthalpy, and entropy. This term needs to be positive. This term is already positive. So I'm going to have a positive enthalpy. For number 8, we're already told that our reaction is endothermic. So that lets me know that my enthalpy is going to be positive. Looking at our change in moles, we're going from 2 moles to 1 mole. So that lets me know that my entropy is going to be decreasing. So now let's figure out our free energy. Will this reaction be spontaneous or not? Well, if I'm decreasing my entropy and I need to add heat, I need to add that energy, this reaction is not going to be spontaneous. It's not going to do it on its own. Only with the help from the surroundings will this reaction ever happen. For number 9, we are told that this reaction is going to be exothermic. So that lets me know that my delta H, my enthalpy, is going to be negative. Looking at our moles or how they're changing, I'm going from 2 moles to 3 moles in total and going to liquid and gas. So that's going to be increasing my entropy. So if this reaction is releasing heat and it's increasing entropy, then this reaction will always be spontaneous. Now for 10, we are given this large reaction, but we are told that it is highly endothermic and very spontaneous. So it's going to be highly endothermic and very spontaneous. Looking at our entropy, well, we're going from solids to, these are going to be in solution. That's going to be a gas, liquid. My entropy is increasing. So if I need to add energy, its entropy increases. How is it that it's going to be spontaneous? Well, in this case, it's all going to be because of our entropy. Entropy is the one that's going to be driving our force for this reaction. Because our entropy is going to be changing so much, it doesn't matter that it's going to be endothermic. It's just going to favor going from that high order to disorder. And that's it. Some of these questions might have been a little bit tougher than others, and that's totally fine. But again, if you have any questions, don't hesitate to ask. I'm here to help. So with that, stay safe, and I'll see y'all next time.